We've mentioned the float data type before. We haven't used it a lot, and we're not probably going to use it a lot in the future, but we have this section here for completeness. We've seen that if you enter a single slash for division, you get a float result, that is something with a decimal point in it. And even if the answer come out to an integer, we still get something with a decimal point in it. And you can, of course, divide more complicated things, and you get an answer that's a float. Now, there's more here than meets the eye. Think about it. Floats correspond to real numbers. There's an infinite number of them, even between the numbers 0 and 1. We can't possibly represent them all in the computer. The best we can do is represent some exactly and only approximate all the others. There's a further problem. I mean, you're used to decimal arithmetic that 2/3, for instance, in decimal goes on with sixes forever. We can never really represent it accurately in our regular decimal notation. In fact, it's even more complicated here on the computer because numbers are not actually stored in the decimal form. They're formed just in base 2, that's in powers of 2, and you can represent some numbers exactly in base 10, like 1/5, but it's not really stored exactly in the computer. In general, the assumption to make about floats is they are only approximate, do not depend on their exact value. We will look at the accuracy more in a little bit. We've talked about creating a float by typing in something explicit or by doing a division. We haven't really talked much about operations with a float. If we operate on 2 floats, we're going to get a float. In fact, if we have 1 float and an integer, we're going to get a float. That is the same for other operations. It doesn't have to be just multiplication. It could be addition or subtraction, for instance here. Even though the result is technically an integer value, it's still represented as a float. Again, the type of these decimals, like 2.5, is float, as we said before. Let me look back at a piece of the tutorial here where I give some idea of where this term comes from. It's basically coming from scientific notation. You may have seen in math or science class that if you have a number like this, you can move the decimal point and put in a power of 10 and get something like this. The decimal point moves or floats around. It's actually a little different with the actual float type, as we said, because it's actually in powers of 2, not 10, but it's a corresponding idea. Let's now look at exponentiation. From math class, you should realize that if you repeatedly multiply, you can write that with an exponent, 3 to the 4th. So let's try this out in the shell. Again, we can't use an exponent in the way we indicate Python, but if you think of exponentiation as a lot of multiplication, the symbol is sort of symbol here, that stands for 3 to the 4th power, which is 81, or 2 to the 5th power, which is 32. You see that it works with integers as well as floats. If you think back to high school algebra, you may have worked with fractional exponents, which correspond to roots. For instance, if we use the half power, that corresponds to a square root. And you see this gives us 3. 3 squared is 9. Or 2 to the 0.5 power is going to be an approximation of the square root of 2. We may find that handy in some places later. Back to the tutorial. You should have seen that Python can generate float values automatically that are pretty big. You're not likely to want that many decimal places. Let's talk about a way of outputting things that is neater with fewer places. Let's consider this shell example. First of all, we've got x set equal to a number with lots of decimal places. There is a format function separate from the format method, although we'll see that it's going to be related. The format function can take a value here like x and then a second parameter which is a string. And the string here represents 5 places beyond the decimal point with those 5 places fixed. If you look at the output from this function, you see it's a string, and it has 5 of the places from the original x. Similarly, if we do the same sort of thing, but with 0.2f, it means 2 decimal places. You notice the 2 decimal places up here are 4, 5, and down here they're 4, 6. The reason is that because of the 7 after the 5 here, with 4, 6, it's closer to x than it would be with 4, 5. This rounds to the closest number with 2 decimal places. Now, this 0.5f and such formats can also be used in the format method for strings. If you look down here further, here's another version of x. And here is a format string. You'll see the format method, and we're going to use the dictionary approach here first, where we are looking at local variables. So what I plug in between the braces here is a local variable x, and now the new notation is a colon here. And then after the colon, we have the same notation as we had in the format function. The 0.5f means this number should be a floating point number, and we're going to represent it with 5 places after the decimal point. And similarly, we could represent it with 3 places beyond the decimal point. Again, there's the colon and then the formatting information. And if you look at the output, you see here we've got the 5 places. Here we've got the 3 places, and you notice that it's rounded again. More on the format method here. You can also use this notation without a dictionary. Here, for instance, where I'm just doing a positional format, I can still put in the colon and the 0.5f, and this will format in a similar way. Let's now go to the other extreme and talk about putting numbers with a great many decimal places. Look at the number 0.1, which I pointed out is not stored exactly in a computer. If we give it 20 decimal places, you see it looks like what you expect, up to about 16 or 17 decimal places, and then it's off. And you can look at 0.2 here, and you look at 0.3. These are all approximations here. Now notice the curious thing because of these approximations. If you look at what's actually stored for 0.1 and 0.2, and if you add them, you find it's not what's stored for 0.3. In a later chapter, we'll get for testing for equality, and basically what that means is, as far as Python is concerned, 0.1 plus 0.2 is not equal to 0.3. As I pointed out, never assume you're going to be exact with floating point numbers. That's the best assumption.